Welcome to DAR Tutors for Online and Home Tuition. In this video, we will explore the fundamental concepts of equilibrium, which are central to IB Chemistry Higher Level. By the end of this session, you will be able to, first, distinguish between homogeneous and heterogeneous chemical equilibria and write their respective equilibrium constant expressions. Second, describe various types of physical equilibria, such as solid-liquid and liquid-vapor systems. And third, understand the concept of the solubility product, which is used for sparingly soluble ionic compounds. Let's begin by defining what we mean by phase and how it helps us classify equilibria. First, let's define phase. A phase is a physically distinct, homogeneous part of a system. It's separated from other parts of the system by a clear, distinguishable boundary. So, what does this mean in practice? Let's look at a few examples. A mixture of sand and water is a two-phase or heterogeneous system. You can easily see the boundary between the solid sand and the liquid water. On the other hand, a solution of glucose in water, or a mixture of ethanol and water, is a single-phase system. This is a homogeneous system. Once the glucose dissolves, the entire solution has a uniform composition, and you can't see the individual components. This distinction between homogeneous and heterogeneous is crucial because it affects how we write equilibrium expressions. It determines which components we include and which we don't. We'll explore this in more detail shortly. Now, let's turn our attention to chemical equilibrium. This is a state where the forward reaction rate is exactly equal to the reverse reaction rate, and the concentrations of reactants and products remain constant. We classify these chemical equilibria into two main types based on the phases of the substances involved. First, we have homogeneous equilibrium. In a homogeneous equilibrium, all the reactants and all the products are in the same physical phase. This means they are either all gases or they are all dissolved in the same solution, for example, all aqueous. Conversely, we have heterogeneous equilibrium. In this type of equilibrium, some or all of the reactants and products are in different phases. A common example is a solid in equilibrium with a gas or an aqueous solution, like a solid dissolving in water. Making this distinction is the first step in correctly formulating an equilibrium expression, as the rules are slightly different for each. Let's begin with homogeneous equilibria. A great example of a gaseous homogeneous equilibrium is the Haber process. In this reaction, gaseous nitrogen reacts with gaseous hydrogen to form gaseous ammonia. As you can see, all three species are in the gaseous phase. Now, how do we write the equilibrium constant expression, Kc, for this reaction? This expression tells us the ratio of products to reactants at equilibrium. For a general reversible reaction, AA plus BB is in equilibrium with CC plus DD, where lowercase letters are the stoichiometric coefficients. The equilibrium constant, Kc, is the concentration of product C to the power of its coefficient C, multiplied by the concentration of product D to the power of DE, all divided by the concentration of reactant A to the power of AA, multiplied by the concentration of reactant B to the power of B. Applying this to the Haber process, we get Kc equals the concentration of ammonia, NH3 squared, divided by the concentration of nitrogen, N2, to the power of 1 times the concentration of hydrogen, H2 cubed. Each species is included in the expression because they are all gases, and their concentrations are all changing as the reaction proceeds. Remember, the square brackets denote concentration, typically in moles per cubic decimeter. Let's look at a second type of homogeneous equilibrium, one taking place in an aqueous solution. Consider the ionization of a weak acid hydrofluoric acid, HF. In water, it establishes an equilibrium with its conjugate base, the fluoride ion, F, and the hydronium ion, H3O+. Notice the H2O-Al. Water is the solvent in this reaction. The rule for solvents in dilute aqueous solutions is that their concentration is considered constant. Since the amount of solvent is so large, any change in its concentration due to the reaction is negligible. The concentration of pure water is approximately 55.6 moles per cubic decimeter, a value that doesn't change significantly. Because of this, we do not include the solvent, H2O, in the equilibrium constant expression. It's essentially absorbed into the value of the constant itself. This gives us a new constant, the acid dissociation constant, Ka. The expression becomes Ka equals the concentration of hydronium, H3O+, times the concentration of fluoride, F, all divided by the concentration of the acid, HF. So, remember this key rule for homogeneous aqueous systems. The solvent, usually water, is omitted from the equilibrium constant expression because its concentration is constant. Now let's examine the other side of the coin. Heterogeneous equilibria. Here, the reactants and products are in different phases. The most important concept to grasp for heterogeneous equilibria is that the concentrations of pure solids and pure liquids are constant. Let's think about why this is the case. If you have a solid, say, a piece of iron, its concentration is determined by its density. Density is mass per unit volume. As long as you have a chunk of iron, the ratio of its mass to its volume is a constant. You could have a small piece of iron or a very large piece. The amount of iron changes, but its concentration does not. This is different from a gas, which expands to fill its container, or a solute, which spreads out in a solvent. Because their concentrations are constant, pure solids and pure liquids are excluded from the equilibrium constant expression. Let's see this in action with an example. Let's look at an important example of a solid-gas heterogeneous equilibrium, the water-gas shift reaction. Here, solid carbon reacts with gaseous steam to produce gaseous carbon monoxide and gaseous hydrogen. Notice the phases: solid, carbon, and gas, all others. Now, which components should we include in our Kc expression? Following our rule, we exclude the pure solid carbon. The equilibrium constant expression, Kc, is therefore the concentration of carbon monoxide times the concentration of hydrogen, all divided by the concentration of water vapor. It's as simple as that. The solid component is omitted. Let's try a more complex example. You'll notice that the principles remain the same. Here's another classic solid-gas heterogeneous equilibrium, known as the iron-steam reaction. Solid iron reacts with gaseous steam to form solid iron oxide and gaseous hydrogen. Once again, we have a mix of solid and gas phases. Let's apply our rule. Which species are pure solids or pure liquids? Iron Fe's is a pure solid. Iron oxide Fe3O4 is also a pure solid. Therefore, neither of these is included in the equilibrium constant expression. This leaves only the gaseous components. Our Kc expression is the concentration of hydrogen, H2, raised to the fourth power, divided by the concentration of steam, H2O, also raised to the fourth power, tau. Notice how the phase of each component is absolutely critical. Incorrectly including a solid or liquid would give you an incorrect expression. So always check the state symbols. We've covered chemical equilibria. Now let's quickly review physical equilibria. These involve a physical process, like a phase change, reaching a state of dynamic balance. The classic example is the melting and freezing of water at 0 degrees Celsius. At the melting point, solid ice and liquid water can coexist in equilibrium. The rate at which ice is melting is equal to the rate at which water is freezing. Another important one is liquid-vapor equilibrium, like bromine liquid in a sealed container evaporating to form bromine gas. Eventually, the rate of evaporation equals the rate of condensation. At this point, the air above the liquid is said to be saturated with the vapor, and the pressure exerted by the gas is called the saturated vapor pressure. This pressure is crucial for understanding concepts like boiling point. A liquid boils when its saturated vapor pressure equals the external atmospheric pressure. It's a key physical equilibrium that we encounter every day. We've reached the 10-minute mark. If you find this explanation helpful and wish to dive deeper into IB chemistry or other subjects, we invite you to contact DAR Tutors for expert, personalized tuition in IB A-Level and IGCSE curricula. Our tutors are subject matter specialists who can provide the support you need to excel. You can find our contact details at the end of this video. Let's now move to a more advanced topic within heterogeneous equilibria, particularly relevant for IB Chemistry HL, the solubility product, CaSePC. Most ionic compounds are not completely insoluble in water. They dissolve to a very small extent and are therefore called sparingly soluble. The solubility product, KSP, is a specific type of equilibrium constant that describes the extent to which a sparingly soluble ionic compound dissolves in water to form a saturated solution. Let's consider the dissolution of calcium carbonate, KCO3. Solid calcium carbonate is in equilibrium with its dissolved ions, calcium Ca2+, and carbonate, CO32. This is a heterogeneous equilibrium because we have a solid in equilibrium with aqueous ions. How do we write the equilibrium constant for this? We apply our rule for heterogeneous equilibria. The KSP expression is the product of the concentrations of the dissolved ions, each raised to the power of its stoichiometric coefficient. So, for calcium carbonate, KSP is the concentration of calcium ions times the concentration of carbonate ions. The solid KCO3 is omitted because its concentration is constant, as we discussed. It's that simple. Let's work through some additional examples to solidify our understanding of KSPO. A key skill is to be able to derive the KSEP expression from any chemical formula. Our objective is to write the solubility product expression for each of the following sparingly soluble salts. We must pay close attention to stoichiometry. First, let's consider silver bromide, AgBr. The solid dissociates into one Ag+ ion and one Bar ion. Both have coefficients of 1. Therefore, the KSP expression is simply the concentration of Ag+ times the concentration of Brs. Now for a slightly more complex one, lead chloride, PbCl2. The solid dissociates into one Pb2+ ion and two Cl ions. Here the coefficient for chloride is 2. This means we must raise the concentration of Cl to the power of 2. The KSP is Pb2+ times Cl squared. Failing to include this exponent is a common error, so be careful. Finally, let's look at aluminium hydroxide, AlOH3. This dissociates into one Al3+ ion and 3 OH ions. The coefficient for hydroxide is 3, so the KSP expression is Al3+ times OHE cubed. Remember to always include the stoichiometric coefficients as exponents in the KSP expression. Now that we know how to write KSEP expressions, how do we use them? The solubility product allows us to calculate the solubility of an ionic compound. A key concept here is molar solubility, which we'll represent with the variable S. Molar solubility is the concentration of the dissolved cation, or alternatively, the number of moles of the solid that can dissolve per liter of solvent to make a saturated solution. Let's calculate the molar solubility of silver chloride, AgCl. We are given that its solubility product, KSP, is 1.77 times 10 to the negative 10. Our strategy is to set up an ICE table, but specifically for a solid dissolving. We need to relate the concentration of the ions to the solubility, S. First, write the dissolution equation. Solid is in equilibrium with Ag+ aqueous and Cl aqueous. We can't have an initial concentration for AgCls in an ICE table, so we'll just ignore it. Initially, we have 0 Ag+ and 0 Cl. Now let's consider the change. If a certain amount of HCl solid dissolves, let's call that molar solubility S. It will produce S moles per liter of Ag+ ions and S moles per liter of Ca ions. This is a 1:1:1 ratio. At equilibrium, the concentration of both Ag+ and Cl ions is S. We know the KSP expression is Ag+ times Cl. Substituting S for each, we get KSP equals S squared. We can now solve for S. The molar solubility is the square root of KSP, which gives us 1.33 times 10 to the negative 5 moles per cubic decimeter. This means only a very tiny amount of HCl dissolves, which is consistent with it being a sparingly soluble salt. Let's work through a final, more challenging example. Our objective here is to find the KSP of a sparingly soluble salt if we are given its molar solubility. The molar solubility of lead iodide, PbI2, is 1.25 times 10 to the negative 3 moles per cubic decimeter. What is its KSP value? We'll follow the same procedure, being very careful with stoichiometry. First, write the dissolution equation for lead iodide. It dissolves into one Pb2+ ion and 2 I ions. Now for our ICE table, which relates the known solubility as to the ion concentrations. The change is plus for Pb2+ because its coefficient is 1. But it's +2s for II, because its coefficient is 2. This 1:2 ratio is absolutely critical. So, at equilibrium, the concentration of lead ions is S, and the concentration of iodide ions is 2s. The molar solubility, S, was given in the problem as 1.25 times 10 to the negative 3. We can now substitute this value in. So, the concentration of lead ions is 1.25 times 10 to the negative 3. The concentration of iodide ions is 2 times this value, which is 2.50 times 10 to the negative 3. Next, write the KSP expression for PbI2, which is Pb2 plus times I squared. Finally, substitute our calculated equilibrium concentrations. KSP equals 1.25 times 10 to the 3 times 2.50 times 10 to the 3 squared. Calculating this gives a KSP of 7.81 times 10 to the negative 9. Again, the crucial step was relating the ion concentrations to the molar solubility S using the stoichiometry of the dissociation reaction. Get that right, and the rest is straightforward. To recap, we've covered the different types of equilibrium. We learned to distinguish between homogeneous equilibria, where all components are in the same phase, and heterogeneous equilibria, which involve multiple phases. For homogeneous equilibria, all species are included in the equilibrium constant expression, with the exception of the solvent in dilute aqueous solutions. For heterogeneous equilibria, we established the critical rule. Pure solids and pure liquids are excluded from the equilibrium constant expression because their concentrations are constant. We also saw how this rule applies to the dissolution of sparingly soluble salts, leading to the solubility product, KSP, and worked through calculations to find both KSP and molar solubility S. You are now able to write and use equilibrium expressions for various chemical systems and understand the principles behind physical equilibria. Remember to pay close attention to phases and stoichiometry, as these are the most common sources of error in this topic. Now it's time to practice. Here are 5 IB-style questions for you to work through. Pause the video and attempt each one. After you've tried them, continue the video for the full worked solutions. Question 1 asks you to identify the homogeneous reaction. Question 2 requires you to write the KSP expression for copper carbonate. Question 3 asks you to calculate KSP from a given molar solubility for a calcium hydroxide solution. Question 4 asks you to derive the correct Kc expression for a solid-gas heterogeneous reaction. And finally, question 5 is a word problem asking you to calculate the molar solubility of silver phosphate from its KSP. Let's review the solutions. Take out your work and see how you did. This is a crucial step for learning and mastery. For question 1, we needed to find the homogeneous reaction, meaning all species in the same phase. Only option A has all components in the gas phase. The others have a mix of solid, liquid, aqueous, and gas. For question 2, the KSP expression for copper carbonate. QCO3 is a sparingly soluble solid, so we exclude it. It dissociates into one Cu2 plus ion and one CO32 ion. The correct expression is KSP il, Cu2 plus CO32, making A the right answer. Question 3 was a calculation. Let's find KSP for CaOH2. The molar solubility S is given. The dissolution is KaOH2S iki Ca2 pleki plus 2OH aki. The equilibrium concentration of Ca2 plus is S, and the concentration of OH is 2s. So KSP is S times E 2S2, which simplifies to 4S3. Plugging in the value for S gives us 4.63 times 10 to the negative 9, which is option B. For question 4, all species are in the gas phase, so this is a homogeneous reaction. This means all reactants and products are included. Following the rules, Kc is the concentration of the products, each raised to its coefficient, divided by the concentration of the reactants, each raised to its coefficient. This matches option A. Finally, question 5. We need to find the molar solubility S from a given KSP for Ag3PO4. The dissolution is Ag3PO4S equals 3Ag plus AQ plus PO43AQ. The equilibrium concentration of Ag plus is 3s, and PO43 is S. So KSP is K3, 3 times S, which simplifies to 27S4. Setting this equal to the given KSP and solving for S, we get approximately 1.8 times 10 to the negative 5. This corresponds to option A. That concludes our deep dive into the types of equilibrium. We hope this session has clarified these important IB chemistry concepts. If you are looking for further support or expert guidance in your IB A-level or IGCSE studies, please don't hesitate to reach out to DAR Tutors. You can find more information and contact us through our website. We are here to help you achieve your academic goals. Thank you for your time and focus. We wish you the best in your chemistry journey.